So in the last discussion, we had covered the first part of this, that is SIP and uh, SIR, basic things, and we have discussed mainly steric inhibition of resonance. Okay, so we have discussed the problems of benzoic acids, and which is also called ortho effect. Now let's discuss steric inhibition of protonation, SIP. And this both steric inhibition of resonance and steric inhibition of protonation, both are useful in describing basicity of amine. So basically the topic is basicity of amine, aromatic amine, that is aniline. This is our aniline. Now before going into that, if I ask you a question, compare basicity of this aniline molecule with simple aniline. Second one is aniline with electron donating group. This type of writing means you can consider it is in ortho position or meta position or para position. And the third structure will be aniline with electron withdrawing group. In a generalized discussion, NH2. So 1, 2, and 3. If I ask you that what will be the basicity order, I think you have thought already, or you have answered already in your mind. So actually the answer is electron donating group will be most basic, because electron donating group will generate more negative charge on this nitrogen, that will repel the lone pair, and lone pair will be more available to attack. So that will be acting as Lewis base. Basically all these three amines will be acting as Lewis base, and electron donating group will pushing electron toward nitrogen, and that negative charge density will be there much. That's why that will repel the lone pair to attack more favorably. Okay, so first will be electron donating group, that means 3, then normal, then 2, then 1. Okay, now the problem arises when in aniline, if I add different groups. For example, it is our cute aniline NH2. Now there is one group. Now what happen if I want to compare stability of different aniline molecules? Then we have to draw its conjugate acid, because it is base. So stability will be decided by basicity will be decided by stability of conjugate acid. So the conjugate acid will be when it will abstract proton, the resultant molecule will be our conjugate acid. So our conjugate acid will be NH3 plus, and this is the group. Now what will happen? Initially there were 2 hydrogen, and now there is 3 hydrogen. If this G group is bulky, then if this G group is bulky, then what will happen? This extra hydrogen will generate an steric hindrance with that G group. Okay, and more bulky the G group is, it will hinder the upcoming proton. So for example, in another case, the G group is very much bulky. Then if the protonation occurs NH3, then it will be very much stable, because initially there were 2 hydrogen and now there is 3rd hydrogen. So there will be too much steric hindrance. So this G group will prohibit this molecule to get protonated. So this protonation will be hampered. If G group is bulky, then it will not allow that this aniline molecule to abstract proton, because abstracting proton will generate a lot of steric hindrance. So basically, steric hindrance of G group is prohibiting the protonation. So it is steric inhibition of protonation. So steric hindrance is basically prohibiting a protonation process. Now, if this G group is not bulky, this is a small group, then there will be no steric inhibition of protonation. Then very finely, the hydrogen can add up here and the protonation can occur. So how will we decide that which groups are uh, you know more bulky or less bulky? If the G group is hydrogen, deuterium, tritium, fluorine, OH, note them down, okay? NH2 and CN. So with these groups, there will be no steric inhibition of protonation. And this similar kind of thing also applies for this ortho effect. If in place of CH3, these groups are there, then also there will be no ortho effect or steric inhibition of resonance. Okay, so now tell me one thing. If there is a more steric inhibition of protonation, let me write. Let's see, if G group is more bulky, G group has bulkiness more, then steric inhibition will be more. That means steric inhibition of protonation will be more. Then this molecule will not like to abstract proton. Then the basicity of this molecule will be lower. So basicity will be lower. So more the SIP, more the bulky the group is, lesser the basicity. So what we can conclude from here is steric inhibition of protonation is basically inversely proportional to basicity of aniline. So basicity of aniline is inversely proportional to steric inhibition of protonation. I hope this is very much clear to you.